Hey guys, Meta has just released the next evolution of the groundbreaking segment editing model called SAM2. This ain't an upgrade. SAM2 takes segmentation to a whole new level, not on images, but also on videos too. Imagine being able to segment anything in any frame across any video, all just with a prompt. In this video, we are going to break down what makes SAM2 so powerful, how it works under the hood, and why it might get game changer for computer vision. Let's get into it. I know that you guys have been requesting a lot more hands-on sessions. So today's session, we will be actually running the whole segment editing model. We will be doing it live and we will run it on CoreLab Notebook. This is going to be a very exciting session. We will be running it on a sample data set, and you will see like how segment editing is able to even segment smaller objects. So very exciting. So watch it till the end. Also, I post regular videos on AI new current topics as well as interviews for Google and Meta. If you're waiting for these interviews, if you are interested in learning about AI, and if you are interested in understanding the basics of machine learning, please do like and subscribe. It's going to be a very exciting channel, and hope you guys enjoy. Original SAM focused on prompt table segmentation and still images, meaning users could provide a prompt. So in this case, the prompt could be like point or a box or a mask. So you have to give an input there. The model would output the corresponding object segmentation. So you can see in the video how it works. However, real-world environments are rarely static, and most visual data in practice comes from a video. Whether it's a surveillance footage or autonomous driving, robotics, medical procedures. So most of the use case for segmentation actually happens for the video. Segmentation in radios introduce a whole new set of challenges. Motion and deformations. Objects can move, rotate, stretch, or shrink. Occlusions. Objects can be partially or fully hidden behind others. Lightning and quality changes. Frames may suffer from blur, low resolution, or even varying illumination. Scalability. Video may be quite big, right? Who can be thousands of frames. So you have to be very careful when it comes to like how efficient you can build this system. Existing video segmentation systems often rely on heavy supervision and task specific. The goal of SAM2 is to build a general purpose model that works across both images and videos, and that can segment anything with minimal prompting. So SAM2 builds on the idea of prompt-table visual segmentation introduced by SAM1, but adding a memory module. So what this memory module does, it's actually stores the objects in pass interactions. So in this way, like it keeps track of what the user has seen, and this allows us to plug and refine objects across an entire video by leveraging memory of previous seen frames. It's actually a streaming architecture that processes videos frame by frame and uses memory attention to revert back to the earlier object representations. But let's say if you want to use it only on images, then you don't need any memory, right? You can it's just one image, so it just works like a SAM1. To support training, the author develops a data engine where human annotators work in the loops at SAM2 to label challenging new data. Unlike most existing dataset, this engine collects annotations of all valid objects, including parts and subparts regardless of category. So if we compare it with the model-assisted annotations, this is actually 9 times faster. The paper also talks about this newly created dataset called Segment Anything Video. So they created 3.55 million masks across 51,000 videos. At the core of SAM2 is a prompt table, a lightweight mask decoder, and it receives the embellings of the current frame, and you can actually generate the mask by providing it the prompt. You can also improve the quality of the mask by adding more and more relevant prompts. So what makes it different from SAM? So the frame embeddings used in SAM2's decoder is not directly from the image encoder. And the main reason for that is because it needs to add the temporal property there. So it is influenced by past predictions as well as prompt frames. Prompt frames could be something from the past or from the future frames through the current frame. It allows the model to retrieve temporal context and prompt-based memory to better handle the object appearance changes over time. There is a memory encoder which processes the current prediction and generates a memory entry for the frame. This memory is stored in a memory bank and made available for feature uses. So whenever a new frame comes, a memory attention operation is called, which retrieves this information from a memory bank, and then it generates the embeddings that is processed to the mass decoder. If you think of it, video could be very, very large. Rather than waiting for the entire video to be uploaded, some could actually those are streaming architecture. So what it means is that each frame is processed as soon as it is uploaded. So it doesn't have to wait till the end. The image encoder is run only once per frame and is responsible for producing decode embeddings for each frame. The model SAM2 uses hierarchy image encoder, which is a hierarchy to vision transformer pre-trained with mask encoder encoding.
Mask encoding itself is a very important part of the Kira paper. So essentially how it works is it's a self-supervised pre-training task where a large portion of the input is masked and the model is trained to reconstruct the missing parts. This is really useful because it encourages the model to learn robust features and spatial reasoning by predicting the content of the masked region. Right, now we're going to go on to hierarchical vision transformer. Now this is an architecture where the input data is processed at varying resolutions, starting with high resolution and simple features, and then moving to low resolution but complex features in the later stage.
Due to its hierarchical design, hierarchy can provide multi-scale features which are specifically useful for decoding objects at different level of details. Let's look at the memory attention mechanism. The memory attention mechanism plays a critical role in SAM2's temporal reasoning. It conditions the feature of the current frame based on the feature and predictions from the past frame, and also new prompts provided by the user. Technically, the memory attention module consists of L stacked transform blocks. The first block takes the current frame embeddings from the image encoder as input. Each transformer block performs the self-attention over the current frame tokens, cross-attention with memory entries from the previous frame and objects, and the multi-layer perceptron for further feature transformations. Both self-attention and cross-attention uses standard attention mechanism. Through the process, the model dynamically integrates relevant context from the past frames and the user prompts to find the current prediction. And nothing really changed for prompt encoder. Prompt encoder is actually the same. It supports a variety of prompt types like points, bounding boxes. You can draw bounded boxes around boundaries or masks. Each prompt type is encoded differently. So there are two kinds of prompts: sparse prompts and dense prompts. Sparse prompts are your points and boxes. It could also be your free-form text, and dense prompts are your masks. So the encoding for those are different. Point and boxes actually extract positional encoding. What it does is basically finds the location of the point, as well as the embeddings learn to distinguish the background as well as the subject. And then the free-form text is extracted using the CLIF model. So it was also taken from a learning transferable region models paper. And masks are extracted using a universal segmentation method. So what it does is basically pass it through a convolution layer to make it 16 times smaller and add it to the element lines with the large embedding. Okay, great. Let's look at the training strategy used for SAM2 model. It's very similar to SAM. The only difference is also train them videos. For the videos, they use frame sampling and prompting. So the idea is that each training sequences consists of 8 video frames, and then they randomly select 2 video frames for prompting. During training, correction clicks are probabilistically added based on the discrepancy between the ground truth, maskless, and model prediction. So the goal is to sequentially and interactively predict the GG mask rate. Look at the dataset for pre-training. SAM2 is pre-trained on the static images using the SA1B dataset, which was actually used for SAM as well. But the difference here is in the metrics. So SAM2 uses Allen loss to better supervise IOU predictions. So IOU is your intersection over union, which is a most common metrics for object detection, and a sigmoid activation function on the IOU object to keep the predictions within 0 to 1 range. For fine training, the data that was used is SAV, which is your new generation video segmentation dataset that they also introduced in the paper. There are some internal video dataset, which are around 15% of the total data, and SA1B, which was coming from SAM1. I think we covered most of the paper. Now let's try to actually code this. So I'm gonna create a collab notebook and let's go. Okay, so we want to make sure that we have the right environment. So I'm gonna click on here to look for the N4 environment, which is correct. So we can confirm this. You can have keep view as well, whatever works for you. So let's do that. So we're gonna look if the environment gets set up correctly. So NVIDIA is the command fodder that shows the what GPUs we have available. So I'm gonna run this anyway. So here I see that bit is NVIDIA Tesla P4. It is available, and that's great. Okay. So I'm cd to the directory. So something that some of these cells are already populated. That's because I entered here just to make sure that I can do the demo. So this one, now it's loading the segment editing project. This is from the meta repo. And then, yeah, it's going to take some time. Okay, so some progress made here. I'm going to get my coffee and I'll be back once this is done. Okay, great. So most of it is done now. Last few seconds, I guess. Okay, great. So this is done. Now it's going to download, install Supervision. Supervision has a library from RoboFlow. This is specifically designed to make things easier for us, especially like invocations or video processing and physically. It's very important. I would definitely use that. So I'm going to install it. It's an open source library. Okay, so this is installed. Now it's going to get the weights of the model. So there are 4 different weights models are available in. You can get the tiny one with just 38.9 million parameters, but you can also get the very large one. So I'm going to use the large one here, and I'm going to just set up all that importing those the libraries. Now setting up the CUDA, this code enables mixed precision computing for faster deep learning. It uses bfloat 16 for most calculations. So this is important because we want to make sure that we have a faster processing here. And we set this up, loading the model. So we, as you can see, we're loading the SAM2 hierarchical had a large model. And this is the configuration. Great. So now it's gonna build SAM2 video predictor. So now we have the model ready, serialized model. Now I'm gonna run. First, I'm gonna download the video. So Met already provides some of the videos for us. So I'm just gonna use existing video. So I downloaded that down over the basketball video. And it's what we get from there. So start up some scaling factors here. So we can see that we need some of the scaling factors to reduce why we have requirements. And this is our target output. So I'm just gonna call it like treasury per code. So now I'm gonna initialize the inference check. So SAM2 requires stateful inference for interactive video segmentation. So we need to initialize an interactive state here. And that's what we had been running on this command. Okay, this is done too. Now just we set the state and encode the image. So we need the encoding because now we're gonna be prompting it with points, or like you can select points, you can select mask, you can select whatever you want. I think third one is the box. So there are 3 objects. Here's ball, player 1, player 2. So I'm gonna specify all of those objects. And then you're gonna use some of the Jupyter Notebook widget. So now you can see that in the image itself, you have multiple objects. So the first thing that we need to do is to mark the correct object. So I selected ball. Now I'm not sure what to do here. So I submitted it. Right. So I need to say, okay, oh yeah, it's here. So now I need to switch to player one. So I'm going to mark player one, and then I must switch to player two. So I'm going to plug player two. And then we set up the default boxes, video and friends. This is the part where it's going to use prompt propagate in video generator. So it's kind of like gonna propagate the whole mask across their video, because we only mounted on an image, right? Or in a frame. So now it's gonna do that. And this is the place where all the processing is happening. So it's gonna generate the mask for you. It's gonna propagate it to the entire video. And this process, guys, is gonna take time. So I'm gonna get my coffee again, a sip, and then I'll be back. Well, still at 9%. Come on. Okay, so we are at 96% now. So almost done here. I'm curious to see what the output gonna look like. And we are getting close to 100%. Here you go. It's all done now, and I'm gonna look at the output. So I'm gonna plot this with the images to show us the mask. Here you go. So it kind of identified these objects and masked them. And over here goes, yeah, annotated kind of. That's it, guys. That's it.